In this problem, we're going to solve linear regression training. So our job is actually to implement the train model function. And we're actually given two functions as it says in the problem description. We're actually given the get model prediction function for this model, which is supposed to be called at every iteration of the training loop. We are also given get derivative. And this is the reason we're given get derivative is to actually perform an algorithm called gradient descent. If you're not familiar with gradient descent, I would recommend checking out the easy problem in this problem list. And there is actually a corresponding video solution that requires zero background knowledge about machine learning at all. But the reason we need the get derivative function is to actually update the weights of our model using the learning rate at every iteration of training. And let's go ahead and check out the inputs that we're given. So the first thing we're given is x. X is our data set for training the model. If we check out the shape, it will have length n, where n is the number of data points in our data set. And it will always, each data point has length 3. We can see that over here. So checking out the example, we can see that we have 2 data points here, right? And each of those 2 data points actually has 3 attributes. So we can see that we have length 3 for this sublist and length 3 for this sublist. So that makes sense given the problem description and the constraints. Then we can check out y. So y is supposed to be the correct answers for our data set, and we should probably have a label for every single one of our data points in the data set. So that makes sense that y's length is also n, 6 is the answer for the first data point, and 3 is the answer for the second data point. We are then given the number of iterations to train for. Essentially, this is the number of iterations to run gradient descent for. We can already kind of tell that whatever the solution is for this problem is going to involve some sort of significant for loop. That's the main part of the solution, and this is the number of iterations to train for. Lastly, we have the initial weights for the model, right? Before any kind of training is done, models, you can still get the predictions from a model based on its current weights, and these are typically chosen completely at random in machine learning. And we can have the initial W1, W2, and W3 given here as 0.2, 0.1, and 0.6 respectively. And since it's given as input to this problem, kind of going to develop this intuition that the initial weights do affect your final weights. And talking about the final weights, that's actually what we have to return. We have to return the final weights after training in the form of a NumPy array with dimension 3. And kind of one last thing to kind of make some sense of this test case is if we check out the problem or the sample data points in X, we can actually kind of maybe guess what the weights should be. So we have 1, 2, 3 corresponding to 6, and then we have 1, 1, 1 corresponding to 3. So we can maybe guess that W1 is equal to 1, W2 is equal to 1, and W3 is equal to 1. This is just adding up essentially the 3 input attributes. 1 plus 2 plus 3 gets us 6, and 1 plus 1 plus 1 would get us 3. So that makes sense that after 10 iterations, our initial weights, they ended up much closer to the final answer, right? 0.5 is closer to 1 than 0.2, 0.59 is closer to 1 than 0.1, and 1.27 is closer to 1 than 0.6. And this is also continuing to kind of reinforce that intuition that gradient descent is just an approximation algorithm. We saw that for the first 2 weights, we didn't overshoot, right? We increased, but we were still less than 1 for 0.5 and 0.59. But for W3, we actually completely overshot, and we went all the way up to 1.27, even though we know W3 should probably be 1, right? So we actually have to perform this for more and more iterations. The number of iterations that you actually have to perform gradient descent for totally depends on the use case. In some case, 1,000 might be enough. In some case, you might need to perform this algorithm for 100,000 iterations. But we are developing this intuition that gradient descent is just an approximation algorithm, and the number of iterations at which you perform it will affect the performance of your model. So now let's jump into the explanation. Now let's talk about the update rule. So gradient descent updates the weights of our model at every iteration. And the update rule for gradient descent, just as a reminder, is that the new weight, or the new W, should just be equal to the old W minus the derivative, specifically for this weight. So the derivative for W, whatever derivative we're talking about here, let's say this was for W1. So the new W1 is the old W1 minus the derivative for W1 times alpha, which is our learning rate and will always be given. And if just for an explanation of why we're using this equation, I would highly recommend checking out the gradient descent solution video. But if this is our update rule, then it's pretty clear that if we're given alpha, right, and we're given initial W's, right, that's actually an input to this problem, our main task at every iteration of this loop, the heavy lifting, is just to get the derivatives for each W. And because we have 3 weights for this problem, we have W1, W2, and W3, we're actually going to need to call the get derivative function, get derivative. We're going to need to call this function 3 times at every iteration of this algorithm so that we can get the individual derivatives for each weight. And if we check out the function for get derivative, we check out what things it takes in. Two of the things it takes in are the current model prediction. So it needs the current model prediction. This needs to be sent in to get derivative. And we also tell it our desired W. So that might be W1, W2, or W3. And then we are also given a function called get model prediction, right? So if we need the model prediction to calculate or call get derivative, then it makes sense that at every iteration, the first step should be to call get model prediction. Maybe we can store that somewhere. Then we're going to pass that into the get derivative function. We're going to pass that into this function, and we're going to call it 3 different times depending on our desired W. And then we can lastly use the update rule and update our weights, and we will repeat this for the number of iterations specified by the problem, and then our training is complete. Okay, so now let's jump into the code. We know that this whole entire algorithm of training is one giant loop. So we'll say like for I in range of num iterations. And we know that to even update our weights and get the derivatives, we need to get our model prediction at every iteration based on our current weights, which I'll keep updating in the variable initial weights. So we can do self.get model prediction and go ahead and pass in x as well as whatever our current weights are. Then we're going to need to grab our 3 different derivatives. So we're going to say that d1, the derivative for w1, is self.get derivative. And let's pass in the model prediction. Let's pass in ground truth, which is just the answers or labels for a data set, which is given in y. Let's pass in the length of x, as that is the n, number of data points. Let's pass in x. And then for our desired weight, we want the derivative for w1, but we can see that get derivative is using 0 indexing, right? So we'll actually need to pass in 0 over here, and that is how we calculate d1. Then we can do the same for d2 and d3. Okay, so now we can actually update our weights based on the learning rates. We can say initial weights at 0 should just be, well, we're actually going to subtract out d1 times our learning rate. So that's self.learning rate. And if you're wondering why learning rate is not given as a input to this function, but instead as kind of a class level hyperparameter, that is just a convention when training machine learning models, especially as we move into PyTorch. So we can say initial weights at 1, then we're going to subtract out d2 times self.learning rate, and finally the same for w3. So we can say at the second index, d3 times self.learning rate. And that's it. We just have to then return the rounded version of our answer. So np.round of initial weights at 5, and we're done. And we can see that the code works. And one test case is enough to verify that your code just didn't get the answer right by a fluke, given that there is some mathematical complexity going on here. So now that we've got the basics down, the next problems that we'll do are going to focus more on PyTorch and starting to train and explain neural networks.